designed the next generation of materials for batteries or all sorts of other components. And recently, as many of you have been working on, actually, machine learning interatomic potentials have been really helping us with this problem. Because one of the grand challenges of this entire digital materials design field has been this multi-scale design problem, which is that we have many individual methods for material simulations, but each of them are only good at certain lengths and time scales. And in particular, ab initio DFT is great at the electronic and atomistic scale. And it's also great because it doesn't require experimental inputs into your system, but it doesn't actually scale towards predicting things like grain growth in metals. Whereas if you look at like a multi-physics or coarse grain type model, you can model things like grain growth, but you need information from the lower length scales fed into the model first. So machine learning potentials have been really a game changer for these lower length scales, I would say. Whereas, typical, MD type methods like Leonard-Jones or EAM would be extremely fast, but be very inaccurate. Whereas DFT would be extremely slow, but actually quite accurate. And then so all of these new kind of machine learning potentials here, and there's so many of them, I'm not trying to pick a specific one, but rather to say that they've now largely achieved both high accuracy as well as high speed. So based on these developments, there have been a lot of claims, as many of you are very familiar with. I'm sure many of you saw this paper from Google Genome where they claimed to find 400,000 new stable materials, and that made a big splash in the field. To compare that to experimental materials discovery, so the Inorganic Crystal Structure Database reports about 10,000 entries per year over the last decade, and the powder diffraction file about 20,000. So 10 to 20,000 is kind of the range for the new materials found experimentally. So if you find 400,000 like actual materials within the span of a year, that's obviously a huge acceleration. And they claim to, expand the space of known compounds by like an order of magnitude or something. I'm sure also many of you saw the MatterGen paper from Microsoft a little bit after that one, which is that you could use diffusion models to generate stable new materials. You could also generate conditional diffusion models to generate materials with specific properties like magnetic density or stiffness, et cetera. And in this paper, Microsoft didn't just compute the materials. They made one of the materials, which is this tantalum chromium oxide, and then they showed that it had high stiffness, which is what they conditioned it to have. So this really kind of set off this imagination that you could, use a computer to just design something in the computer, and then out comes like a game-changing material in the lab. So I think you've seen a lot of this news recently with tons of funding in this area. Lila just recently raised about $350 million. They also do biopharma. Periodic Labs here in the Bay Area just reported $300 million in funding. This is largely for just materials design and the types of ideas we've been talking about. Orbital Materials now $200 million, Cusp.ai $100 million, Radical AI, which I'm on the advisory board for, $50 million. So there's certainly a lot of money being allocated to this idea of computational and accelerated AI/ML materials design. But even a lot of people that are supportive of the field as a whole are pushing back. So, there was this article in Nature about, are any of these materials that we dream up good? There's millions of materials generated. Are they actually useful? There was a professor at UC San Diego, Anthony Cheatham, very famous professor there, that, kind of pushed back against a lot of these stable materials results. Even, Jonathan Godwin, who is working for DeepMind and then worked for Orbital Materials, which is one of the startups in this area, felt that they were maybe overblown in some of the claims about new stable materials that we got. There were also reports that a lot of these new materials that were being generated or predicted were not actually new materials. There were things that were synthesized before. And in some cases, these new generated materials that were, the kind of the showcase pieces were things that were even in the training data itself. There have been people within these companies, like Entalpic, again, is one of these startups funding on this company, that look at their competitors and say, how did they raise $300 million on a pitch deck? These are like Periodic Labs is probably what he's referring to there, and they don't have a product, they don't have any material, but they have $300 million. And to be fair, a lot of these people are pro AI materials design. They really agree with the vision, but they just feel like things are getting a bit out of hand and that more common sense is needed. So what this talk is about is over the last 20 years, I feel like I've been in the space. I've done a lot of, these kind of theory to experiment to kind of patenting materials type exercises for batteries, thermoelectrics, catalysts, et cetera. And when I see the field, I feel that certain types of problems are being attacked quite a lot. Things like machine learning potential development, while other topics are maybe not being discussed enough, but are important for the field as a whole. So I just kind of want to talk about those things and maybe give a few examples of things that we've been working on in this. So in this field, we see a lot of this type of pipeline where there's some kind of a theory or AI/ML model that predicts the material and gives you the correct target for a specific application. Then there's some kind of robotic synthesis or automated lab that figures out how to make that material and gets you somehow like a pure sample of it. And then there's going to be some type of automated characterization or maybe manual characterization that gives you like a consistent and clear outcome of the properties of that sample. And then the assumption is that if you get a lab scale success, that we can scale it up without too many modifications. And so there's a lot of talks kind of about success stories through parts of this pipeline. I think this one is going to be more like all the stuff that goes wrong and things that can derail this thing and make you not get all the way to the commercial success. All the things that prevent you from getting all the way to market penetration. You might still be successful getting from theory to synthesis or synthesis to characterization, et cetera. But there's a lot of things that just derail you across this whole thing. So I want to start by talking about the theory coming up with targets for synthesis. And what I wanted to do was maybe walk through a pre-AI/ML project that we did in terms of finding new thermoelectric materials, and just tell you what we did and what kind of results we got. And then I want to kind of go back and say, if we went back in time, but we had all these AI/ML tools, would it have helped us be more successful in this project? And if not, what were the tools that we actually needed in order to be more successful in finding new thermoelectric materials? So this was our approach on the right that we were doing before all the AI/ML stuff really took off. Okay, so a quick introduction. So thermoelectrics are devices that convert between electrical and thermal forms of energy. Most popularly, they use thermal gradients to generate electricity. So there have even been companies spun out of UC Berkeley actually to take industrial waste heat and then put that through a bunch of thermoelectric modules and recover electricity. This had some success in like remote areas and things like that, but I think the company eventually went under. But anyway, there's still a lot of research interest for space applications as well as other things to convert waste heat into energy. They're also in niche devices. You might buy like a wine cooler that uses like thermoelectric cooling to cool your wine and keep it at like a very stable temperature while not making a lot of noise and stuff. Okay. So we've steadily been finding more and more materials that have thermoelectric properties, and ZT is the metric that you use to look at the figure of the efficiency of a thermoelectric. And over the years, experimentalists have been finding more and more high ZT thermoelectric materials. And one of the interesting things about this field is that you can get lots of different types of crystal structures. You see like simple rock salt and derivatives like Voisler antifluorite, kind of very simple crystal structures working. You also see very like complex structures working like this iron 4 Se3. You also see all sorts of chemistries that are potential thermoelectric. So it's not just like a section of the periodic table that's interesting. So there's like a pretty wide canvas for materials that could be thermoelectrics and a very high design space. So even like over 20 years ago, people were saying, computing is becoming very inexpensive. Maybe you can run these like multiple test tube reactions as a way to search for new thermoelectric materials. And you might be able to complement between theory and experimentalists to find high ZT materials more quickly. So if we want to screen for thermoelectrics computationally, we have to understand the metric that we're looking at. Academically, we typically just look at ZT, high figure of merit, although in practical thermoelectric, there's a lot more things that are important. For this to be a success, we should probably target a ZT of at least 1. 2 is, really more of like a breakthrough thermoelectric material. And the components of the ZT are materials properties like the Seebeck coefficient, which tells you how much voltage you get for a certain thermal gradient, the electrical conductivity, and those two things together, the voltage and the current, basically give you what's called the power factor. And then you want a low thermal conductivity because that maintains your thermal gradient for your material. So these are the components that we need to predict about a material if we're going to predict the ZT. All right, so what should we do? We should get some big compute. Yeah.
If your ZT is always proportional to T, why don't you just report the Z?
Yeah, so the Z part usually peaks at a certain temperature, and then the T will, of course, increase with temperature. So there is usually a temperature at which ZT itself peaks. And then, the temperature, so depending on the application, if it's industrial waste heat, let's say the output flue is at like 800 degrees C. So you want to kind of constrain the T to 800 degrees C in that particular case. It doesn't really help you if you have a 1200 degrees C material. And then finally, a lot of materials just start breaking down at really high temperatures. So, you can't just increase it indefinitely. Okay, so we know what ZT is. Why don't we just get some computers and just start calculating ZT for a ton of materials and just figure out the best ones and then like solve this problem, right? But the problem is that in most materials simulations, there's no quantum operator for the exact materials property that we want, in this case, ZT. I can't just say, let me run a DFT code and just get the ZT out. Instead, we have to design how are we going to actually get the ZT and what approximations are we going to make. And so there's a lot of work in designing the actual framework for getting the ZT. So here's that ZT equation again. It's written in a slightly different form, but I just want to go through the different terms here. So for example, for the Seebeck coefficient, actually there are codes that can take the DFT output, in particular the electronic band structure. There's a code called Boolstrap that can give you the Seebeck coefficient pretty good to first order, as long as your band gap is pretty okay, which is not always the case in DFT. But that's actually one of the most straightforward ones. N is the carrier concentration in your material. And we have no real way to predict the carrier concentration in a material. We just can't get it. There's a lot of studies where like, given a known carrier concentration, we do some like doping calculations and defect calculations, and we try and like justify why we couldn't dope it or why we can dope it. But in terms of like predicting, like here's a random material, what is the carrier concentration you're going to get? There's nothing that really exists like that. So what we're going to have to do is just optimize ZT as a function of the carrier concentration and just say, here's like peak ZT, right? And we'll re-examine that later. The mobility is very difficult to calculate explicitly. Again, you don't just get it straight out of your calculation. In particular, the electronic scattering portion of this requires lots of additional theories on top of your DFT simulation. So you have to figure out exactly which approximation you're going to make to get the mobility. You can do just constant, and every material is going to have the same exact scattering time. You can come up with semi-empirical models that are maybe fit to some experimental data, where you calculate some other descriptors like the bulk modulus or the band effective mass, and then add some like exponential terms that you fit, and then see whether you can use that as an approximation. So there you have to make these decisions. And then for the lattice thermal conductivity, the explicit calculation is difficult. And so again, you have to figure out like what approximations you're going to use and just kind of go with them. So we have to do this. And so here's the approximations that we picked. Doesn't matter. But the main thing is to know that we can't just get the property directly out of the calculation. Okay, so with the framework in place, now we can start doing some computing. At that time, we started with 50,000 materials in materials project. We calculated the electronic transport properties. We generated about 300 gigabytes of electronic transport data, and then we made that all available, and then we started looking for thermoelectric materials based on all the data that we generated. So let's skip to some of the results. So one of the ones we found is this thulium silver telluride. This is a material, this is the electronic band structure, and this is not the density of states. This is the power factor you get as a function of the Fermi level. And so we want high power factors, without going too far into the bands. So we thought this one was interesting because there's two crystal structures, and regardless of the one that we made, it could actually have interesting thermoelectric properties. We also found that this one, we didn't know if it was going to be N-type or P-type because we can't predict the carrier concentration, but both of them looked like they could be pretty interesting. And then our experimentalist colleagues have been working a lot with silver telluride compounds, which they knew had low thermal conductivity. So that gave us a little more confidence in this as well. The only issue is we found that it needed 10 to the 20th per cubic centimeter carrier concentration to hit the peak in power factor. And again, these are like strongly peaked power factor functions. So you kind of have to like hit the doping pretty well. So the ZT that we got, which we thought could get to like maybe 2 or 3, which would have been a great thermoelectric, the ZT that we got was only about 0.35. And the thermal conductivity was low like we expected. but we couldn't get the carrier concentration that we wanted. So we got only about 10 to the 17th. So we got, we didn't hit the peak in the ZT. We later found better ways to dope it, and so we got a peak ZT of 0.47. But again, we never really got to what we needed in terms of the doping in order to get this to be really high ZT material. We tried a related compound called yttrium copper telluride. This one we thought could have a ZT of around 1 at first, but then we later did the calculations with spin orbit coupling included, which is not typically done in these databases. And then we found that actually reduced the power factor in the ZT by quite a bit, the effects of spin orbit coupling. So anyway, experimentally, we got a ZT of about 0.75, which again is close to the one that we were targeting, but still far from anything that would attract like a ton of commercial interest or anything like that. And so, we got decent performance, but we didn't really see a path forward for this one. And we had a lot of other hits too, kind of in a similar vein. We found some phosphide materials that, typically are underexplored as thermoelectrics. We found some of them could actually have pretty high ZT, but, nothing again that was like really, really earth-shattering. So, although we got a lot of good papers out of it, I think our collaborators were pretty happy that we were able to show this whole pipeline. We never really hit the initial goal of ZT greater than 2, and we didn't find anything of like commercial value. So let's go back and see like what might have derailed the screening, because we tried 50,000 compounds. So if I go back and I say, what is the stuff that that really made this hard? One of them, the first number one is probably the carrier concentration. We had no way to predict for any given material, whether it be N-type or P-type, or what the actual concentration of dopants would be, despite the fact that the properties peak sharply with the concentration of doping. So usually there was some kind of like dopant killer defect that prevented the doping that we wanted, and we had no way to predict that in advance. So that was probably number one, the thing that we were missing. Number two was probably the mobility. So I mentioned that we modeled the same electron scattering time for every single material in the data set. And what we got was a lot of these like false positives where we had these really flat band systems. And flat band systems tend to have higher scattering rates, which reduce the electron mobility. And so because we didn't model the fact that the flat bands are going to have lower electron mobility because of higher scattering, we got a lot of these systems that looked like they were interesting, but if you were to actually make them, they would be like bad conductors. So we had to like manually filter all these systems out and be like, okay, this looks like a flat band system. Yeah.
So if your band structure really changes and you set, but the mobility also depends on the band. So this looks like constant mu, and this thing seems to be contradiction.
So sorry, can you say that again?
Well, if your band really varies, your mobility should vary.
Yeah.
And so it seems almost an inconsistent assumption that mu is constant if your band depth varies so much.
Yeah, and so for example, in the electron mobility, there's the effective mass of your electrons. That is modeled by the band structure. We take the curvature of the band structure, all that stuff. But then there's also the scattering time of the electrons. And that one should be modeled. We should say that, okay, if you have really flat bands, we have actually higher scattering rates. But it was not modeled because there's no easy way to say, how do I take this band structure and estimate the scattering time, right? So we just took a constant for everything. And again, that led to all these false hits. So, whenever you have these descriptors where you're not directly calculating the property of interest, but using some kind of an approximation or some kind of downstream theory, there is the fact is you're going to get false positives, false negatives, and things coming out of that. And so that's what we saw here also. And then probably the number three reason was the accuracy of the band structure calculations. Things like spin orbit coupling, which typically aren't done in high throughput. Van der Waals corrections, which typically aren't done in high throughput. The functional they use for the band gap, all that kind of stuff was probably the third thing that derailed it. So what if we went back and we said, okay, now we have the fanciest machine learning potential that exists today. Could we have gone back and like found the greatest thermoelectric? So here's my opinion. So sorry, this is a busy slide. Number one is the doping. There's no training data right now for doping of materials. And in order to actually do the calculations correctly, you need to do what are called charge doping calculations with higher levels of theory and these image charge corrections applied, et cetera. These are not in the machine learning potentials today. So I have like zero confidence that they'd be able to predict doping. Even though they could give you answers quickly, I don't think they would give you accurate answers. So I don't think that the machine learning would have helped us with this predicting of doping today. Maybe they could in the future if someone actually generates a great doping data set. And Materials Project has tried actually for many years. Other people have tried at NREL for many years to get this doping stuff in line. It's hard, and more people need to be working probably on that. Okay, electron mobility. So the machine learning potentials don't give us the band. We need the band structure for the electron mobility. There's just no way around it. Machine learning potentials don't give us the electronic band structure at all. So it would not have helped us in our previous study. Now, the scattering time, as I mentioned, there are some models that use things like the bulk modulus and other materials properties to estimate the scattering time. So maybe they could have helped us in that sense, where they could have given us the bulk modulus, much more quickly. That is something that they can compute. And we could maybe have come up with some ways to estimate the scattering time a little bit better. But someone have to come up with the theory of like, what is the scattering time as a function of the bulk modulus? Okay, the accuracy of the band structures was the number 3 reason. And again, the machine learning potentials just don't give us the band structures at all. And then other factors, I would say the machine learning potentials would be most useful for predicting the lattice thermal conductivity. That's something that they can do today. A lot of people are actually using this to get the lattice thermal conductivity. But that was never actually a problem in our screening. We always got materials with very low thermal conductivity. We didn't have a problem with that. So yes, they could have probably given us better lattice thermal conductivity estimates, but I don't think it would have made like a practical difference. So I think the takeaway from this section is that a lot of times when we talk about computational material screening, we talk about like machine learned potential accuracy, plus like the fanciest structure generation algorithm, plus like throwing a bunch of GPUs at the problem. But I would say more often than not, we actually run into theoretical limitations rather than like the simulation accuracy limits. So we had another project on batteries. One way to design a great battery is to have one transition metal transfer 2 electrons. And we had all these candidates of materials that could potentially do that, but there's no theory that tells us which materials can actually do this and which materials don't. You just have to throw it in, make the material, throw it in the lab and see what works. And if there were a theory that would tell us in advance, then that would help us. But there's no theory, so there's no way to simulate it. There's no way to predict what an actual material that's synthesized will look like. Is it going to be N-type? Is it going to be P-type? What kind of defects will form? Will the layers mix together the ions or will they not? That kind of theory is needed. Recently, there's been a paper about new metal alloys that are resistant to high temperature oxidation. At the beginning of their paper, the first paragraph is that, let's see, there is, sorry. No accurate predictive simulations capabilities exist for either of the two properties at present. The community still relies on disruptive observations. So the beginning of their paper just basically says there's no theory for predicting the properties of these alloys. So I guess my whole spiel here is that there's a lot of room in translating what I call translational theory from the simulation computables, things like the total energy and the forces and the band structures and all that stuff, to getting to the engineering properties that we care about. There's still so much work to be done there, and I don't think that should be neglected. Okay, so we talked about some of the ways the theory to synthesis part can be derailed. So the theory can be inaccurate. There can be a misaligned framework to go from the theoretical property to the engineering descriptor. We talked about the scattering time, for example, being the thing that was misaligned. The modeled system can be different than what was the actual system that was made in experiments. And then also critical properties like, the carrier concentration might not be modeled at all. Okay, so let's talk about synthesis. So let's say you assume you have the correct target. How do we get to the synthesis part? And there's a lot of papers now that predict new stable materials and say, I've predicted more stable materials than the previous thing that predicted the most stable materials. And there's really no great descriptor, honestly, from computations to tell you whether a stable material is actually realizable in reality. So the one that's typically used is what's called energy above the hull. And this is a paper previously done largely by Geert Sater's group and Wenhao Sun that looked at this energy above the hull descriptor and how well it discriminates between hypothetical materials that don't exist and observed polymorphs that do exist. And there's clearly some signal there where low E above hull compounds are much more likely to be observed materials than hypothetical materials, but there is quite a bit of overlap. And even in very simple binary material compounds where everything that's going to be made has probably been made, when you look at the E above hull descriptor, the blue ones are the ones that have been observed, the X's are the ones that haven't. There's a ton of stuff that you would think would exist theoretically, but that are never going to be made experimentally. So we can easily make predictions about materials that are stable, but we're not going to really know which ones are truly observable in reality. So, this is not the only descriptor. There have been a lot more ones. Veer has stuff. Other people have things as well. So I don't want to go through all the history of that. But I do want to say that, we've been looking at a different way to do this, which is to look at, yeah.
A late question. So your DFT calculations are usually zero temperature state.
Yeah.
So how do you even know that? So stable means zero temperature state. How do you even know this is sort of 5 Kelvin stable?
Yeah, so you can what's typically done is you can add temperature dependence for vibrational entropy properties. So basically the temperature dependence of the thermodynamic stability comes from the entropic properties of your materials, the entropies of your materials. So there's different components of your materials entropy. There's like vibrational, electronic, configurational, etc. So people have done these sorts of things for the vibrational entropy, which is probably the most important one to do for these things as you move to finite temperature. So that lets you look at these thermodynamic stabilities at finite temperature also, and not just at 0 Kelvin. But you still see the same thing. You still see tons of overlap, even when you adjust the calculations for finite temperature and vibrational effects. It doesn't solve this problem where you say, just shift the E above hull to 300K or 400K or target temperature. It doesn't seem to solve it. Yeah. Okay, so if the bottom-up theory is difficult, can we take a top-down approach, which is to start with all the known synthesis recipes and come up with some models for which materials might be synthesizable, how much you make them? And so the Sater group and our group had been working to collect a bunch of articles, about 8.8 million articles on material science, and create various different data sets about solid-state synthesis reactions. So the one on the left is about gold nanoparticle synthesis, and that had about 1,000-ish records in it. And the one on the right is about solid-state material synthesis, like powder synthesis, and that one has 40,000-ish entries in it. And so the goal is there some signal in this data set that will tell us what materials might be synthesized, how might we make them? Unfortunately, when we look at the data, it's actually extremely messy, incomplete, and non-randomized. So on the left is some results from our gold nanoparticle data. And what the numbers are is the completeness of the data, meaning what fraction of the recipes had this data. So on the bottom left, where it says seed solution 61%, that means 60% of the papers that reported a recipe for gold nanoparticles reported what the seed solution was. And 40% of them neglected to mention the seed solution. So if you look at like how many of them actually mention the seed solution and the growth solution, it's like only half the papers actually tell you what they used for the synthesis. And then that plus the characterization is like 40%. So, it's very common that key synthesis variables are missing from these papers. The other thing is, sorry, it's very hard to see on the screen, but the other thing is that the outcomes, mapping the outcomes, which is like whether you have a pure crystal or an impure crystal, in this case for bismuth ferrite, as a function of all the input variables can be extremely complicated. And the interaction effects of the chelating agent and dehydrating agent, surfactant, all this stuff, it can be very unclear. And, often you see weird things like, for example, citric acid, acetic acid, surfactants, the goal of all these things is to reduce the amount of impurities that you get in the final bismuth ferrite sample. But what we see in the statistics from our literature is that the ones that were solvent only actually had a pure crystal at a higher fraction of the time than adding all this other stuff that's supposed to be helpful. So, these sorts of going through the literature can be tricky. We looked at, for example, gold nanorods. On the y-axis is the aspect ratio of your gold nanorods. Are they long and skinny, or are they like short and squarish? And on the right is the concentration of silver nitrate you used in the solution as you made the gold nanorods. And the known rule of thumb is that if you increase the silver nitrate concentration, you get higher aspect ratios. That's what you expect. When we look at the data, we just see like a big mess of points across the literature of like reported silver nitrate concentrations and the actual aspect ratio that was reported. The ones in circles are ones where like it looks like all the experimental variables that they reported are basically the same except for the silver nitrate concentration. So we tried to like control for all the other stuff, and we still don't see any like real signal in the circle points. In fact, at one silver nitrate concentration, you see like multiple circle points. And everything looks the same as far as we can tell in those reported recipes, and you get like every single aspect ratio under the sun as an output. So it's really hard to get like predictive models out of these text mining models. Here's one that was also done in collaboration with Theta Group, where we looked at synthesis prediction models. And this was for solid state synthesis. We were trying to predict what temperature should we react these precursors at, and for how long should we react them in order to get our product phase out. And so we had this data set that I mentioned of solid state reactions. So we tried to, come up with some descriptors based on the precursors that were used, and then use that and the target as well, and then try to use that to create, in this case, both a linear and a gradient boosted tree model in order to predict the temperature and the time the reaction to react the precursors to get the output. And so again, what you see is tons of scatter. I mean, the left is a synthesis temperature, the right is a synthesis time. It's really difficult to make a predictive model with any sort of like tight accuracy for synthesis using this top-down approach, because the experimental data is just extremely messy. So we were thinking maybe we can kind of bring the bottom-up theory along with the top-down approach to help us interpret the data. So we've been starting along that approach. Here's one analysis that we did along that line. So we wanted to see solid state reactions that resulted in impurity phases, because typically we don't want impurity phases. So could we predict which reactions might have impurities based only on the thermodynamics and looking at the literature data? So what we did is we identified in the literature data two types of scenarios. On the left is a scenario where starting from the precursors, your impurity is more thermodynamically favorable compared to your target. On the right is a scenario, all the scenarios in the literature where your precursors, your target was more thermodynamically stable than the impurity. So these are all recipes where impurities did form. So we expect this situation to happen a lot more than this situation in the literature. And so we found that a little bit. We found that on average, because these are all formed impurities, on average, things were kind of 20 MeV per atom more on this side, and there's certainly more data points on this side than we have on this side. But certainly there's a lot of cases where the target is like significantly more thermodynamically stable than your impurity, but we still see the impurities forming. We also started looking at things like how precursor choice affects the formation of certain targets. So here's a target, which is titanium-3 aluminum carbide. And we have different choices of precursors that we can mix together in order to achieve this target phase. So we can start with the elements and start reacting those. We can start with the binary titanium carbide and react those with the elements, or we can start with this Ti2AlC compound and then react that with titanium carbide. These are all different routes towards achieving this target. And what we find is that the fraction of phase pure outcomes that we get is very different depending on the precursors that we use. So if we start with the elements, we only have about 50% of the recipes reporting phase pure outcomes. Whereas if we start with these, this almost fully reacted material, we see that almost all the recipes that start there actually end up with the phase pure material. So we can do things like look at the starting components and the final component and look at the thermodynamic landscape on the phase diagram and see why we might be seeing certain impurities. So if you start with the elements, which are on the vertices of this triangle, what you find is that the most thermodynamically stable next product in this 3D landscape is this titanium carbide compound. That is the most that has the highest driving force for reaction. So if you start with the elements, you might get stuck in this titanium carbide result. Whereas if you were to start with these two endpoints, Ti2AlC and titanium carbide, if you look at the thermodynamic landscape there, what you see is that actually the most favorable downhole outcome is your target phase, this Ti3AlC2. There's really nowhere else for this reaction to go. And so that's going to give you, certainly better outcomes. So, I didn't have a chance to sketch this out in greater detail, but certainly you can imagine this as a scenario where there's an AI/ML agent. It has access to all the literature data. It has access to theory simulation tools, maybe to map out these thermodynamic landscapes. And it can be connected to, autonomous robots. And, you can imagine some kind of MCP with this AI/ML agent to the literature data. And you can chat with it, ask questions, see what are the ways that things have been made before, and then use that to control the robot. So that's one of the things we're working with Theta Group on that in the future. Okay, so we talked a little bit about the synthesis part and how it can be difficult to find a synthesis route. how getting phase purity can be difficult, and how even the same recipe can result, or seemingly the same recipe can result in like really different outcomes. I think anyone that's been in the lab knows that sometimes somebody else in the lab can make a material and then you try to like make that same material and you just can't do it. Or you read a research paper and you try to reproduce a synthesis. Anyway, these are all things that are practically important. Let's talk about the characterization part. And, AIML can help there too, but it's maybe less talked about, I think, than the theory and the synthesis portions. So if we have automated labs, we can generate tons of samples. But the problem is every single one of those samples needs to be characterized, right? Because we can just generate a ton of powders, but that doesn't help you. You have to know what the powders are, what their properties are, et cetera. And traditionally, we didn't have that many powders or that many samples. So you could one at a time have an expert analyze that sample. But now that we have like hundreds of samples, you need to have like hundreds of high throughput characterization going that an expert can't just like look at every single one. So to that end, we've been trying to develop other better ways to do automated interpretation, in this case, the powder X-ray diffraction patterns. And one of the tools that was developed there is called DARA, again by Gerard Sater's group. And what they do is that typical X-ray diffraction powder phase identification algorithms will kind of do a linear procedure to try and get you to the phase mixture based on the XRD pattern. But what this does is it actually creates a tree of possibilities for different types of different types of compound mixtures that could fit your pattern. And then based on it'll try to prune down that tree and try and figure out the best kind of combination of materials and phases that fit your pattern as best as possible. And there's something called refill refinement to further get you like a good fit to your sample. So these sorts of new softwares are certainly needed. And in their initial tests, they did a bunch of solid state reactions. They had a bunch of these powder X-ray diffraction patterns. They had human experts try to fit the patterns. They had this DARA software that they developed to fit the patterns. And they had kind of the industry standard, or one of the industry standards called J, try to fit these patterns. And they looked at the fraction of patterns where they could fully index the pattern, meaning that all the different peaks in the pattern were explained by the compound mixture that they determined. And they found that, okay, DARA can actually fit the XRD about as well as a human, meaning, they can get all the peaks, accounted for about as well as a human. And so that was a pretty good result. And, the RWP, which is another measure of goodness of fit, also matched the human one. But we've been trying to deploy this in practice with Lauren here for one of our collaborations. And we've been seeing sometimes some weird results, which is that the best fit result is not always a good interpretation. So here's an XRD pattern, and this is the best fit result from DARA. There's no other fit that's better. So if you can do all the numerical optimization in the world that you want, you're not going to find, let's say, a better fit than this one. The problem is that this outcome doesn't make sense. So this has calcium carbide, the CaC2, as one of the predicted phases. And under these synthesis conditions that I've listed here, the carbide is not going to be reduced. There's going to be some oxygen attached to it. So what would normally be done at a one at a time characterization is that an expert would look at this and say, this one doesn't make sense. Let me move on to the next pattern and see if that makes sense. And if it does, then I'm going to accept that pattern. Unfortunately, again, you could do all the numerical optimization that you want. You're not going to come up with a way to do that. So what you need is a way to automate chemical intuition. And one of the things we were doing is testing whether LLMs have this kind of chemical intuition that they can use to interpret XRD patterns. So what we did is we provided the LLM with synthesis precursors and a procedure. We asked the LLM to rank the likelihood of a synthesis outcome, and then we gave it some examples and things like that. So we said, given these synthesis conditions, does this make sense? And so, for example, for that calcium carbide example, we asked it to rank the relative likelihood of different phases to be there. And calcium carbide is at 0.1, so unlikely. Calcium vanadium oxide, which is actually likely, is 0.6. And then the mixture of those phases to be probability of about 0.3. So it seems to be having the type of chemical intuition that we were looking for, that we could kind of automate high throughput. So what we did is that, given an XRD spectrum, we first used the DARA software to enumerate all the different trees and subsets of combinations of phases that might be there. We try to fit them as best as possible using the DARA software. But then we add another layer on top, which is this AIF, or artificial intelligence framework, that tries to look at other things like, well, how likely chemically is this to exist based on composition balance and LLM likelihood and things like that. And what it will do is it will try to predict a probabilistic outcome of interpretation 1 seems the most likely, interpretation 2 seems the least likely, and each of these interpretations are a mixture of phases that could be there. And then also for each of the phases, how likely are each of those phases to exist? So we did 20 XRD patterns with 4 evaluators, and then we asked the evaluators, do you like the result from the automated interpretation framework, the AIF? Do you like the one from the DARA, which is the lowest RWP? Do you like both of them? Do you like neither of them, et cetera? And so they definitely prefer the one from the artificial intelligence, which was used to kind of re-rank the numerical scores to ones that had chemical intuition in it, to ones that just didn't have any chemical intuition involved at all and just was a straight numerical score. They also did
For clarity, A, B, C, and D are for human.
for human. Yeah, these are for humans, right? There is actually a lot of inter-annotator disagreement between the 4 humans, which is also interesting, but I didn't touch upon. Yeah, that's something that we're also looking at for sure. We have the matrix of all the agreement between the annotators, and it's not good. Yeah, I mean, Lauren was one of our chemists, BIDMaP fellows. I don't know which letter you are. One of them was someone that had a lot of experience in solid state synthesis, and 2 of them were our collaborators at Twitter Research Institute. But honestly, 2 of them I think come from more of a computational background than an experimental background. Nevertheless, they were what we had available. Okay, we also were looking to design a trustworthiness score so that poorly fit patterns are flagged, because again, neither is a big category here. So, I don't know if we can get rid of the neither, but we can hopefully flag the neither. So we look at things like the LLM likelihood of an explanation, the entropy of the interpretation likelihood. So if there's lots of different interpretations, but they're all similar in probability, then we have less confidence that one of them is correct over the other. Composition balance, other things as well. But the idea is that we want the chemist trusting the results to match whether our framework trusts the results. So yes, no is good, and off diagonals are bad. And we are getting pretty good results there in terms of telling chemists when they can trust the results. We also more formally looked at something called the Breyer score, which looks at our predicted confidence versus like a 1-0 about whether it was true or not. So it penalizes high confidence bad answers. It rewards, you could be low confidence and wrong, but that's good. So anyway, our Breyer scores, lower is better. So our Breyer scores are definitely better than like uniformly trusting things, as well as using like an average trust of like 0.7 or something. So this seems to be working a little bit. We also, once this framework was in place, we actually reanalyzed some patterns that were already analyzed by DARA. And then we found that a lot of things that the chemists initially didn't like from the DARA results, when they re-reviewed the AIF interpretation, they found a new interpretation that they did actually like. And then a lot of times where they didn't get a different interpretation and they still didn't like it, we were able to tell them that the trustworthiness of that interpretation was incorrect. So I'm running out of time, so I won't go through this plot in detail, but we are like preparing all that stuff. Okay, so we talked about theory, synthesis, characterization, all the things that can go wrong. I think I'm probably running out of time though, right? Do I have, how's the time going? Oh, I have 9 minutes, okay. Okay, I'll go quickly through the last part, which is, let's say you get all this stuff working and you have lab scale success, and we have a lot of frameworks for that, which is really useful. What about this last mile, which is getting from lab scale success to market penetration? And there's a lot of materials. I mean, I know a lot of BIDMaP works on MOFs, and MOFs were discovered lab scale success, Nobel Prize, but the market penetration is still, not quite there yet. It might take a few more years to really get high market penetration of MOFs. So what about all this other stuff? So let's say you find a great new catalyst. It actually theorized it, you got it working in the lab, and you actually show that it works, and you have like a great result. You have even a powder of that catalyst that you can provide to like your industry partners and be like, hey, look, this is a great catalyst. What is all the stuff that goes from a powder to what's called a technical catalyst body? And this is like a little pelletization of this. And you might be somewhere here where you've done idea synthesis, screening, characterization. Maybe you've even done some of the mechanism and kinetic studies. But what actually does it take to get all the way up this chain. And the thing is, there's a lot of other steps that we don't ever really talk about. For example, we always say that, okay, we have the research catalyst. We got a Nature paper out of it. We're kind of done now. But one of the things you might need to do, for example, is figure out what is the trade-off between mechanical strength and activity of your catalyst. Because on the left, there is the porosity of your technical catalyst, of your little pellet. If you have higher porosity, your gas can diffuse through your material. You can have better catalytic activity, but your mechanical strength is going to be low. Whereas if you go the other way, then you can have high mechanical strength, but now the gas can't get into the catalyst. So you have to first do like all these experiments to figure out what is like the relationship between your porosity and these other properties, and figure out like, okay, for my downstream plant, what is going to be the best optimal trade-off for my pellets, or do I have like a mixture of pellets or whatever. Then once you've like identified, let's say, that porosity, you have to figure out in your chemical process to make this technical catalyst, how am I going to achieve this porosity? So in this case, you might add a porogen, like cornstarch, somewhere in the middle of this like synthesis thing, and you have to figure out exactly where to put it. And then in the case of porosity, you have to add a thermal treatment at the end to remove this porogen and leave just the voids in your material. And that thermal treatment might mess up your catalyst. It might mess up anything else that you've kind of put inside this technical pellet. Because there's all these different additives like porogen. This is the one that I talked about. We have to figure out the porosity and add the process. You have to do that for all these other things. And this might be like 70% of your catalyst. So you have to, there's a lot more stuff that goes on that we don't necessarily talk about. But if we want to get all the way to like societal change and like market penetration, we have to solve these problems too. And just the last thing that I'll say is that, we often compare materials commercialization to pharma as being like, long development timeline stuff. But, the people that have studied this, they find that pharma patent value peaks about 10 years after discovery. Whereas for materials, 10 years is just like you're getting warmed up. Like that's where you're getting warmed up with the value of your patent. And then, 18 years is where it's really going to take time to mature. If you look at PVC, for example, one of the big issues was just getting the code approvals for PVC. At first, it was commercialized quite early. You get like they're in chemical plants, typical factories. But then before you could put them in buildings and vents and things like that, there have to be like hundreds of code approvals that happen. And that again took like decades. So that's the type of problems that need to be solved if we're going to get all the way to like societal change. Okay. So quick takeaways. Number one, more theory. We need more theory. MLIFs are great. They're already changing screen discovery. It's wonderful. People are coming up with more and more better and better MLIFs. But we need better theory. Many applications need better theory, even more than better MLIFs. LLMs are making it really easy to extract material synthesis data sets, but they're still super messy. And we need better ways to kind of make use of that data. Automated labs are going to need automated characterization. And if you need intuition, then LLMs might actually have that intuition. And then finally, commercialization has a lot of other problems that we're not really solving, I would say right now, too much with materials AI and ML. And it might be difficult because a lot of the data sets that we need for scale up and composite design and all this other stuff are likely to be sparse and proprietary. So we should be thinking about that more as well. So with that, let me thank all the people that have been working on this, as well as the funding from Department of Energy, as well as Toyota Research Institute, and take any questions.
Wonderful. I have a lot of questions, but I'll just ask you one. You mentioned issues with the quality of the data, and that's something that I'm kind of pretty concerned about, because this kind of data is so scarce and so difficult thing that you kind of inevitably have to rely. Humanity has spent a lot of time building these data. Problem is, the previous figure of merit for that data was, is it published? And then once it goes into, once it's a bullet and somebody's CV, good for you, you get a cookie, your H index goes up and you move on, right? Now we need to go back to all those bullets or CVs and ask, are they worth anything? And we don't know how to answer that question. What's your take on that? Because if we start training these models with this mix of really good stuff and pure garbage, just that got published, right? We're going to have a hard time. And your plots on those, on getting predictive models out of these scatters were a very sharp expression of that.
Yeah, I think it's been discussed a lot. And there are probably technical solutions to this now where you could probably, upload a paper and there could probably be an LLM that just checks to see whether your synthesis recipe is complete. Is it missing the growth solution? Is it missing the seed solution? There's probably technical solutions now that could flag the missing parts of your data and the quality of your data. But I think the social aspects are still the unsolved portion because, are we really going to enforce and say you have to go back and add all this data? I've also heard of cases where people intentionally change or leave out things in their synthesis recipes because if your group is really the top group at synthesizing a particular material, you want to maintain your competitive edge. I've heard that there are cases where they intentionally leave things out or whatever. So these are social. Yeah, exactly. So there are social challenges as well, and that I have no idea how to solve those portions of it.
But do you then think that we should look at this as only new data moving forward? I'm kind of wondering, what do we do with whatever hundreds of years of chemical data we have out there in order to show that we are using right now, we're trying to use?
Yeah. I mean, okay, so there are definitely things that can be done. So for example, I've been working with a group that does sol gel synthesis. And they were recently trying to target a material and they were trying to make this, and it has a lot, like all the synthesis methods, it has a lot of parameters and knobs that you can tune. So it took them 3 or 4 months to figure out how to make this material. And then we had this synthesis data set that we compiled, and then we sent it to them and they looked up this material. They're like, oh, it's actually in your synthesis data set. It's very similar to the recipe that we ended up with. And so there's already a discovery problem where people that are trying to do syntheses need to find the most relevant previous recipes. And I think that problem can be solved relatively soon. I mean, just again, hook up an LLM MCP server to synthesis data set, chat and say, has anyone made anything like this? What would you recommend? And give it like a list of papers. I think that can be already pretty helpful. But then maybe new data needs to have a new set of quality standards than the old data.
So, sorry, there's a message over there. Maybe it's a question or something.
How do
Can you just,
I don't know how to do it. Sorry. Okay, yeah.
It's your computer.
Okay.
That's sorry.
It's like a Zoom thing, right?
Yeah, there's probably a
There we go.
question in the chat. Oh, yeah. Sorry, guys. Sometimes people on Zoom are forgotten, so maybe should be okay.
So I'll read the comment. It says, can you comment on materials discovery, not screening, using generative models, particularly conditional generation? Are validity rates enough to characterize the materials and do new conditional generative models predict materials with correct properties to a good extent? So, I talked a lot about starting with a set of materials and screening down to the materials that are good. Can you just condition materials and generate materials like a MatterGen type? I haven't played around with these models a lot, so I can't really tell you the answer. I will say that from what I've heard, they struggle to come up with complex materials and that there's a lot of stuff that comes up that is maybe not good. So, I haven't quite seen great examples of conditional generation of a truly new material that has functional properties. The one even that MatterGen reported was something that was very similar to something in its training data set. So, I think long term, this is going to be great, but I think short term, I'm not sure that it's like practically really, really useful right now compared to starting with materials with known recipes and trying to find new uses for them.
So maybe you have to for one more question. Sorry, guys.
Professor, that's only years in I have a two-part question. The first one is like, what do you think is probably the next big material that's coming and you think will scale up? And it kind of how to change the society, the next big thing. Secondly, what is maybe the most exciting kind of subdomain or area of materials where you feel like innovation here would truly revolutionize or change things? So one's more the next thing, and the ones that are what are you most excited about?
Yeah, I mean, the next big material is anyone's guess. Again, there's a lot of materials like perovskite solar cells that are starting to really make it to market. I mean, they're starting to hybridize them with silicon solar cells. and they're getting really close to being in market. I mentioned MOFs, and again, they're not quite there yet, but they're starting to get there in terms of market penetration and things. So I'm not sure there's going to be anything that just like shows up and then all of a sudden within 3 years has like transformed everything. But there's certainly a lot of things that have like been on the journey for 10 years now, and I feel like they're starting to get close to making it. And hybrid perovskite solar cells, I think, are one that's you're gonna start seeing them in products, and people are gonna start buying them like in bulk relatively soon. In terms of like what is the topic of material? I mean, I don't know if there's one that I would say is like, okay, you should go work on this right now, because that is like the place to be. I tried throughout the talk to give multiple different places where there's still gaps remaining. And I think any of those places would be great places to get started.
So, guys, in the interest of time, maybe let's thank you again. So, thank you.